Welcome to our webinar. GH2 India is an industry association focusing on the green hydrogen and the P2X sector. We work very closely with stakeholders across the ecosystem, right from manufacturers of technology, the producers of green hydrogen, ammonia, methanol, and the rest of the P2X product commodities, policymakers, financiers, and the consumers of these energy sources or chemicals that are produced as a derivative of hydrogen. We work very closely not just with stakeholders within India, but also because India is relevant across the world. We work a lot with our international partners as well, be it consumers in Europe and Asia Pacific, providers of technology across different countries, and most importantly, policymakers as well, as an enabling force within this entire ecosystem. So it's my pleasure to introduce Alois and Paulo. Alois and Paulo are based in Santiago, Chile. Paulo is a digital leader at Hinicio, and Alois is a senior software engineer at Hinicio. What we're looking to do over the next hour and a half in the webinar is introduce you to Hinicio's product called ANDREA. We are collaborating with Hinicio to spotlight their flagship simulation and optimization platform that's getting increasingly relevant, not just in the Indian context, but globally as well. Hinicio is a leader and a technical and strategic consulting firm within the hydrogen and the sustainable mobility space, and have developed ANDREA, which is an advanced optimization and simulation tool tailored for the PTX projects. This tool has been under development since 2021, and ANDREA has empowered the users and clients to efficiently model complex system architectures, customize solutions, and derive strategic insights, which are crucial for the techno-economic, commercial, and operational success of such projects. These technologies are critical in converting renewable energy into versatile fuels and chemicals downstream. We've seen the development of such projects accelerate in India over the last couple of years, and it's delightful for me to introduce this particular tool with Hinicio to all of the project developers and the manufacturers of technology in India who might be users of this tool going forward. This webinar involves an interactive demonstration of the ANDREA tool, showcasing the features and the functionalities, how this tool can facilitate data-driven, intelligent decision-making, and optimize project performance, especially in the Indian context. We hope this gives you all a good feel about ANDREA's applications across various sectors, including mobility and transport, ammonia, electrified fuels, and chemicals production. Let me pass it on to digital leader Paulo and senior software engineer Alois at Hinicio to take this webinar forward. Thank you. Paulo and Alois, over to you.
Thank you. Thank you, Arjun. Can you hear me well? Perfect.
Yes,
so
Paulo.
First, thank you so much for inviting us to collaborate in this webinar. We really appreciate the opportunity to present the work that we have been doing for the last year, and we are very happy to be able to participate here. So the idea is that we're going to start with some slides to provide a little bit of context about Hinicio and about the work that ANDREA does, and then we're going to jump to a live demonstration that will be guided by Alois. That's going to present all the capabilities and features that you can find in ANDREA. So, Alois, can you confirm that you're seeing my screen?
Yes, we can see it.
Perfect, thank you. So, the starting point will be to give some words about Hinicio for the one that doesn't know it. So Hinicio is a strategic technical consulting firm specialized in hydrogen and its derivative, sustainable mobility and industry decarbonization. So we have a wide range of multidisciplinary team of consultants that really helps to get along with all the projects that we do. And we have a lot of experience in all the different parts for the hydrogen industry. We have closely collaborate with governments, company, and international organizations. And we have offices in Brussels, Paris, Rotterdam, Santiago, Bogota, and Washington, D.C. And since 2022, Hinicio is part of the Vulcan Group, a big engineering firm based in France. Going forward, The business line that we have or service lines that we have are five. So with this, we cover everything that is needed for project development and also for the support on the different part of the different companies, including policy, regulation, and so on. So these lines are business and strategy, all related to understand better what the industry of hydrogen is. So we have also a line that's called project development assistant that is to support the development of projects for client. We have investment advisory, policy and regulation, and the last one, this one was launched last year, is digital solution. That is the one that gathers us today. That is about advanced tools that will help to move forward with projects. And the last few words would be Inicio has a global presence together with Vulcan Group. We have developed more than 800 studies and projects in more than 35 countries, including India, some of them. Okay, good. So starting with the introduction of today for the Andrea, I would like to start with this figure that is, we could say that it's a summary about the project development journey. I will assume that most of you know a little bit what it is about, but the idea here is that in the x-axis we have the timeline, in the y-axis we have the cost of a project, and we also have a line that represents the risk. So the overall idea here is to understand that the initial phases of the project up to or before feed, one expect to spend like 50% of the total project cost, and then to decide how to move forward. And the important thing is that during this time is where the risk has to be managed. And also, this is really important because having a robust project or background is really important in order to avoid going after FID, because if the project is not robust enough, you are not coming back the project and realize that it's not good enough or the business case is not strong enough. After FID could be really, really expensive. So having everything together, everything sort before is really, really important. I think that's why we want to focus in this part. So from scoping to the feasibility up to fail free is where really the most of information or all the risk and the most of the risk of the project has to be managed. And for doing that, there are different work streams, and each one of these work stream have their own challenges and so on. But in this opportunity, we are going to focus in two of them: the technical design and the commercial regulatory. And why is that? Because due to the characteristic of the hydrogen industry that is constantly shifting with the policies, new technologies, and so on. The challenges about this are really, really important in order to have a good system design and also in order to manage all the risk inherent that have in this kind of industries. So, and to understand that, we have these figures that is more about the traditional project development and the power to X project development, because there is a shift here. We can see that in the traditional way, we have more a linear approach, meaning that we have like clear paths that or we know that we have to follow in order to reach or in order to be able to develop a project. And this is because the industry in which and the market in which these big chemical facilities were being developed, the information was they have more than 30, 40 years of experience. So they have a lot of information. They know how the market works, they know the regulation well. So developing that project has the tools to be able to follow this linear approach. But in the Power 2X cases, it's quite different because this is an evolving industry. We do not have all the information available. We do not know what will happen in 5 years, in 3 years, actually, in some cases. So being able to be flexible is really important. And also this demand to have a system approach, a system thinking, meaning that each one of these variables that we have here, for example, the operational design, the plant capacity, the policy and regulation, certification, and so on, if you change one, it's going to affect another one. So this really put a challenge in terms of how I design my system in order to improve my business case. So because everything is connected together, and one small changes in one part could be really affect the other one. So this different approach that you need to develop projects really put some challenges here. And for this one, at the end, we understand that this is translated to a mathematical problem. So we know that we have a problem that we need to solve, but the path to do it is not clear. And based on that, we develop an approach that combines methodology, and software. So in this triangle, summarize really well what we're trying to transmit here, in which we can find that what is important here, that more than focus in one single variable, is to try to maximize the project value. And how we can do that? So in each one of the vertices, we have like the most important aspect that we need to check or to consider when we try to maximize this value. That is the system design and cost optimization, and the market and willingness to pay, and the regulation and certification. And when you combine two of the vertices, you move around the lines of the triangle, you're going to see different things that's really important also when you start to develop this kind of projects. For example, if you combine system design with the market and willingness to pay, you're going to find the game between prices and structure that you are going to find in your project. If you combine, for example, regulation certification with the market and willingness to pay, you are going to be able to define the attributes that your sustainable products will have. And if you combine regulation certification with the system design, you're going to find the operational design. So how my system has to operate in order to be able to get this product. So and the center, all of it, we have the maximum project value. Why this? Because it's not always that the project with the minimum levelized cost is going to be the best. Not always to produce only sustainable product is going to be the best. Not operating always following the renewable core is going to be the best. It's really a combination about the cost structure, the technologies that you have available, the market that you're targeting, and the regulation, the certification that you're trying to include into your system, what is going to drive which one is the best project for you. And in the center of all of this, we have Andrea, because Andrea, it's a tool that we're presenting today that really has the capabilities to combine all these different variables in order to understand what are the systems that are able to feel or to follow these different guidelines in order to find this system or project with its value maximized. So a little bit of the methodology and the tool. In the methodology side, what we propose always to solve this kind of problem is the system engineering methodology. And this methodology is quite standard, but the good thing is that it can be fit to almost any kind of problem or challenges that we face. And it's based in three main questions that always has to be answered. And those are what, which, where. For what, we are referring of what I want to do with the project. For example, it could be I want to use electricity to produce hydrogen and to produce a derivative. You don't have to be like more or more detailed in that phase. But then you go to which, so you start adding a little bit more definition. You start taking out some degrees of freedom of your system in order to start defining it. So, for example, which technology I'm going to use? I'm going to use wind farm, PV plant, I'm going to use alkaline electrolyzer, I'm going to use PEM electrolyzer, and so on. And then the last one is the where. So I have to locate everything that I'm going to do in a physical part, meaning that what is the, for example, where I'm going to locate my chemical facilities is going to be near the power production, the electricity production is going to be near a port. I'm going to transport everything. I'm going to have like a big pipeline, a big transmission line, and put all the chemical facilities near the port, etc., etc. So there is a lot different scenarios, and this is well represented in these figures that we have below here, because this show more or less how the projects are evolving. I'm starting from a central idea. I want to produce, for example, stuff, and then you start analyzing that if I want to produce stuff, you have different alternatives, different options, and so on. And each one of these points at the end represent a scenario or a case that you can you can have based on your initial statement. So, and the important thing is that in each one of these points that we have here, scenario cases, a different business case can be done. So you really need to understand the figures, the market, and everything about the project in each one of these stages. And for that, we use Andrea. That is the tool that we have here in the right. So Andrea is the tool that we have been developed since 2021, as what was mentioned in the introduction, and actually it's the same tool that we use in our own studies. And this is really important because we understand that in this industry that is shaping every day, it's evolving every day, the flexibility is key in order to be able to address all the challenges that arises almost every day. So that's why Andrea, more than a modeling tool, I like to say that it's a framework tool because it enables the user to build an unlimited kind of system, models, and so on, because that provides the flexibility needed in the industry right at the moment. So some figures about the tool. With Andrea, we have more than 4,000 hours of calculation. Andrea has been used in more than 100 projects, including high power to hydrogen, ammonia, e-fuels, mobility, chemical, uh, and others. Also, in Andrea, we have modeled more than 9,000 cases in the last 4 years. And to finish the introduction and to start with the fun part of the live demonstration, I have here an example of how this methodology plus the tool can be used in order to optimize or to find the how to maximize the value of a project. So here we have a typical project that you can find in which a wind PPA is going to be used to produce hydrogen, to produce ammonia, and then to produce a green ammonia or FMBO ammonia that is able to participate or to be transferred in high willing to pay market. And for doing that, the best case, if you want to maximize the value on the speed restriction, so follow the figure that we have here. So the idea in this case is that you try to use as much as possible your renewable electricity to produce as much as possible hydrogen, as much as possible green ammonia or RFMBO ammonia. But if you want to do this, you have to highly oversize your electrolyzer to be able to use as much as possible as electricity, meaning that also that you are going to find some hours in which all your system is going to be underutilized. But it could perfectly fine also this. There's no problem. But there's more alternative at the end. So for example, what if we reduce a little bit the electrolyzer size and we also fill the gaps where it's not using the electrolyzer with electricity coming from the grid. So now instead of only having our FMBO product, maybe I can have also now a low carbon product. And why it is better or worse than the previous case, we don't know. It's really depending on what you're trying to do with your system. But the important thing to understand here is that, for example, here you have reduced capex. Maybe you are going also to produce less amount of RFMBO product, but you can compensate this reduction with another kind of definition or product. So it's not better or worse. It's really that you have to analyze both cases to understand what are the differences between each other to really understand which one is the one that maximize the value of your project. And also it could be more complicated. For example, instead of starting from a greenfield project, maybe you can have a brownfield. So you have an existing steam machine reforming, you have already consuming natural gas, maybe you have access to biomethane, and now you want to include this in your value chain to produce different products, and now you can have maybe with the same system to produce three different things. So at the end, it could be really complex, and the important thing is to understand how to manage the risk in this project and how to get the right information that are going to allow you to take a informed decision to move forward with your project. And I think with this, I close the introduction and we can jump to the live demonstration. So please, Alois, the floor is yours.
Thank you, Paolo. Can you confirm that you can see the screen, please?
I can see it.
Yeah, perfect. So thank you for the introduction. So now we jump directly to ANDREA, so for a live demonstration. So first of all, just to add a few details regarding ANDREA. So ANDREA, it's a full web-based tool. So everything to work with ANDREA, you just need to have a computer and a web browser. You may, of course, to analyze and to input data, want to use also Excel files, but you just need basically a web browser. So we'll start first, before entering to the use case, I will start to do the live demonstration. So here I have some folder, and I will show you to create a case and to analyze and how quick we can have the basic finding of the case. So we'll add a new case. I will write it base case. Then when you add a case, you have the possibility to change some general parameters. So the lifetime of the project, I will leave it at 30 years, the discount rate 8%, and without inflation in this case. I will just change the year parameters. I will start the investment in 2027 and the first year of operation 2030. So this means that I will start to invest in all of the equipment in 2027 during 3 years, and the project will start the operation at 2030. So during those 3 years, I will have to pay equally the capex of all of the component and then start the production. And I will let it in US dollar. I will save it. Now we can directly go to the case. So as I started as a blank case, so I have nothing. So I will, before explain to you all of the parameters that we can add, I will start directly to import a case. So I will go to a standard collection and I will select a full case. And for the live demonstration of today, so I will just select the Power to Ammonia project. So here we can review the description of this case. So I will not go into the details, but we want just to produce 1 million of metric ton of ammonia per year. And as a disclaimer, all of the data that are present in the standard collection, so all of the data that we'll show you today, are just representative and do not have to be treated as real data. So I will import the case. So this is now all we can see. So here we have, so in the standard Power to Ammonia, we have a photovoltaic and a wind farm. We have the possibility to use a grid take or pay. So all of them are the input of electricity. Then we can see that we have an electrolyzer here. I will open it. So we have the electrolyzer that produces hydrogen consuming water. The hydrogen can be compressed, stored, and then go into the Haber-Bosch process to be exported at the end. So here, as I imported out of the case, I can now show you the meaning of each tab. So the first tab is the carrier. So I will close this one. So in the carrier here, we can define all of the elements that will be exchanged between the component of the case. So here we have, for example, the ammonia. We leave it with the physical unit of tons of ammonia. We have the electricity. We have different hydrogen, just to be sure to separate the hydrogen that is from the electrolyzer and the one from the storage. This is mainly just for post analysis after that we can do. And we also have the water. So here, according to the scale of the project, we can change the unit just to be sure that the number that we will input it will not be high or very low. So here I will just leave it in as we want to produce million of tons. So we know that we will be in gigawatt scale. So I will leave it in megawatt hour for the electricity and tons of hydrogen. Then once we have out of the carriers, so we can also, of course, add a new one. I will show you after the first optimization what we can do. Then for the supply, so the supply at the are all of the components that bring carriers to the system. So they are important because this is a way to introduce to the system some of the carrier. For example, here we can see that we have tree of electricity. So we have the photovoltaic one. So we can open it and show all of the parameters. So the carrier that will be produced by this equipment is the electricity. We have general parameters that are the same as the base case. We also can account some integration on a cost or contingency that will be added on top of the capex. And in this case, we are assuming that we will build the PV plant along with all of the other component of the project. So we consider that we have a fixed capex, so a capacity capex in terms of US dollar per megawatt of capacity of the equipment, and OPEX as well, expressed in US dollar per megawatt, but per year in this case. So all of the other parameter can be left empty. In this case, we just leave also to be consistent with the technology, we leave a yearly degradation of 0.5% per year. I will show you the wind farm is the same, except that the capacity, capex, and OPEX are different, and we did not use any degradation for this case. So just a comment on the grid. So the grid here is considered as a take or pay. So it means that we inputted a fixed capacity OPEX. So this means that we will have to pay the same amount of OPEX per year of this unit just based on the capacity. So in this case, we can represent a take or pay. So this is assuming that we will have to pay 80 US dollar per megawatt hour, but in a take or pay way. And the water supply, in this case, we just consider that it's pay as consumed. So we just have to pay 5 US dollar per cubic meter. So all of the data can be changed. Of course, we can start to add fixed capacity, maximum or minimum capacity, or to tweak some advanced parameter as well. But for now, I will leave it everything as in the template. So after the supply, we can have the converter. So I will start by the electrolyzer. So a converter, it has the same general parameter as the supply or all of the other components, except that for the technical input, we now have to specify the carrier that enter the converter with the efficiency. So in this case, we'll consider that the electrolyzer will consume 50 megawatt hour 11 cubic meter of water to produce 1 ton of hydrogen. So this is the conversion that the electrolyzer will have to use for each time step of the optimization. We also consider in this case that we'll have 1% of degradation just for the electricity part. So we can, as you can see, we leave it empty for the water. So we just consider that for each year, we'll have to increase the electricity consumption to maintain the same production of hydrogen. So I will leave the capacity economics are the default one as well, and we have no other technical parameter for this component. The only one is that we consider that we'll have a replacement of 30% of the capex at the middle of the lifetime of the project. So this means that at this year we'll have to incur 30% in repex for the component, and we will bring back the efficiency, the electrical efficiency, to its original value. We also consider here, so we can change this parameter, that the degradation, so the 1% of electricity, only affect 95% of the total electricity. This is to represent that the stack degradation, so the stack consumption of the electricity, this part is only 95%. So the 5% represent the balance of plant, and this will not be subject to the degradation in this case. But we can input any value between 0 and 1% and 100%. So we'll continue by the compressor. So the compressor just use 1 ton of hydrogen from the electrolyzer as input, electricity, and produce hydrogen at 200 bar. And we just have capacity, capex, and opex in this case. So the Haber-Bosch, at the difference of the electrolyzer, so we also have the electricity and hydrogen as an input to produce 1 ton of ammonia. And we also consider that in this case, it has a technical minimum of 30%. This means that this plant cannot operate below 30%. And we also activated the flag that this plant should be always on. This means that we cannot shut down for any time step of the simulation this plant. We can also, of course, change it if we want to consider the possibility to shut down this plant or not. But for the live demonstration, I will leave it as always. Then I will continue with the storage. So the storage are as well the same general parameter. So we need to specify some behavior of the storage. What is the carrier that is stored? So in this case, it's hydrogen at 200 bars, and the carrier that is discharged. So we wanted to make the difference. So it's hydrogen at 30 bar, but from the storage. And we have, as it's a storage, a lot more of technical parameter very related to storage. That in this case, as it's an hydrogen storage, they are mainly left empty. But for example, as we will see in a base, we want to have those parameters. So we can change the charge and discharge efficiency, charge and discharge rate. We can also add a self-discharge. We can also control the initial, minimum, and maximum state of charge if we want to go deeper into the analysis of the component. So the ammonia is the same, so I will not enter into the details. And so the last component is the demand. So the demand in this case is the opposite of the supply. So it's the component that will extract from the system the carriers. And in this case, as it was mentioned in the description of the case that I imported, we want to extract 1 million of ton of ammonia per year. So we have less technical parameter as default, so we can input a revenue if we want, but in this case, we just fix the total amount of ammonia that should be produced. So now I will go back to the representation of the case, because as we said, so the electrolyzer produces hydrogen at 30 bar, the storage as well, but from the storage, and the ammonia consumed, so if we open it, hydrogen 30. So we needed another kind of component, that is this one, that is the mixer, that has less technical parameter, but this component is very useful because it allows us to consider two carriers that are similar and to be treated at the same. So in this case, we consider that if we have hydrogen at 30 bar from the electrolyzer or hydrogen at 30 bar from the storage, it should be treated as hydrogen at 30 bar. So this allows us to mix in any kind of proportion for all of the hours the hydrogen and to leave it like that. So the Haber-Bosch can consume from any one of the sources. So the last tab, sorry, is the profile one. So it's very important because as we are dealing with renewable profile, so with renewable energy, so we want to be able to fix some behavior in early resolution. So in this case, in this tab, we can upload. So I will just show you. So we can upload, for example, a file with the profile, and then we have the profile to be attached for the component. In this case, we have a photovoltaic profile that has been attached to the supply PV, so the photovoltaic one, and this represents the maximum operation. The same for the wind. So depending on the component itself, we can attach to a profile that represents several configurations. In this case, we just have operation max. We could change it to restrict a minimum operation or to match exactly a fixed operation. So as we are considering an operation max, we will allow the system to have curtailment for this profile. So I will just show you the early repartition of both of them. So here are the profile. So we have a early profile, a typical one for the photovoltaic and for the wind. Now, let's go back here. So now, I have my case. But what I want to do is I want to participate to a tender. And this tender, so for this tender, I need to produce 1 million of ton of ammonia. But I will not have the exact same configuration. First of all, I do not want to consider the water supply as a contract because the tender imposed me to have a desalination plant. So how can I do it? So this is quite simple. I go here and I completely delete this component. And I will browse in utilities and I will go to add a desalination plant. So here I can review the name. So I will have a supply that will be the sea water, and I will have a new converter that will be the desalination plant. So I can see what was the carrier saved with this. So the output curve was determined as water. I will just remove, and I want to keep my one. That was the water. Okay, perfect. So now, if I look at the desalination plant, so I have electricity consumption, I have the water from the sea, and I produce water. So perfect. So I will just move it to organize a little bit here. Okay. Now save. So I also want to be able to account separately the electricity from the photovoltaic, the wind, and the grid. So I will just have to add new carrier, electricity. I will put grid, renewable. Okay. So now I will change. I will say that the photovoltaic is not producing electricity anymore, but it will produce electricity, the renewable one. I will do the same for the wind. And for the grid. So the grid will use electricity from the grid, of course. So now I have a problem because I have nothing consuming this two new electricity. So those units, the supply that produce this specific kind of electricity are not used. So we just have to add a new mixer, and I will call it electricity mix. And that will produce the electricity. So where is my mixer? My mixer is here. I will just organize a little bit. And now I will trick the system to say that electricity from the grid or from the renewable plant can be treated as electricity from them. So this, why it's important? Because now I can, for example, if I have some specification into the tender, I can activate the advanced parameter of this mixer and start to restrict the proportion, so the minimum, the fixed, or the maximum proportion in a hourly or in the resolution of the profile, or in the total for the whole year. In this case, I will leave it empty. But for example, we could fix, if the tender specification says that I cannot use more than 20% of grid electricity per hour. So I will discard, and I will leave it empty. Okay, so now I have my electricity. I have my hydrogen with the desalination plant, as the tender said, but the Haber-Bosch, as you can see it, so there is no nitrogen that enter because it's considered that there is an integrated air separation unit. But and so I have a selected Haber-Bosch, and in my data sheet I have a separated air separation unit and a cooling system. So I will just delete this equipment and the same. I will import, so I will go to the standard, I will go to the derivative, and I will select the Haber-Bosch, but the details, model one. So we can see out of the carrier and just import. Okay, so my Haber-Bosch is not there. I have my air separation unit and my cooling system. So now we can see that we have an electricity consumption from the air separation unit that produces nitrogen. We have a specific cost per ton of hydrogen, and we also have in the Haber-Bosch now, we have a consumption of cooling, of thermal energy for cooling. So 1 megawatt hour in a thermal unit. So I needed a cooling system. So I also have a cooling system that will consume electricity and water. So now we can consider that this should match the tender specification. So now we need to optimize to see what will happen. So I will, once everything is set up, I just go to optimize. Then I can again change all of the general parameters if I want. And I will just leave everything empty. I will select as a main carrier the ammonia. So in this case, I have no option because it's the only demand carrier that is extracted from the system. And this is only to the automatic levelized cost calculation. So I will go to optimize. And now it's optimizing. So it should take 1 minute or something like that. So I will take this time to explain you what is happening right now. So ANDREA, so the optimization framework, converted all of the restriction and input data that was present in the case into the mathematical representation. This mathematical representation goes into our Hinicio server, and it's solved by an industrial mathematical solver that we use Gurubi, but as you saw in the previous windows, we can change it to make the exact optimization of the case. So by optimization, it's important to mention what we are optimizing. So we are trying to minimize the total cost of the system. So all of the capex, opex that are present into the system with the technical restriction that we have. In this case, so we have few technical limitations. First of all, we have the renewable profile that show us the maximum amount of production that can be used per hour for the photovoltaic and the wind. And we also have the restriction that the demand should be, so the production of ammonia should be 1 million of ton per year. Okay, so it finished. So now we can see that it's that the optimization finished. So just to terminate, to finish in the explanation. So we had this limitation that was 1 million of ton. So this, in this case, we had all of the component with empty size as input of the optimization. It means that we wanted to size all of the component of the system, knowing that we want the minimum cost and we want to produce 1 million of ton of ammonia. So we can, of course, completely change the focus of the optimization by starting to fix size of any of the component and see if how much we can still produce with this component in fixed size. But first of all, I will go to show you some result. So now that the case has been optimized, we can go and see the result. So here we have the quite the same representation of the case, but in here we can only see the components that were part of the optimum solution. And now we can also see the main characteristic, so the main result of each of the components. For example, we can see that the photovoltaic, the optimum capacity of this plant is close to 2.3 gigawatts of capacity, that the wind plant is 1.5, so we are like close to 4 gigawatt of electricity from renewable, and that the grid take-up pay is like very small. It's like 35 megawatt and almost used in base load. We can see and review the capacity of the electrolyzer. So it's 2 gigawatts. So we are like half the capacity of the renewable production, and we have a capacity factor of 50%. So this view is to have a quick understanding of the main capacity and operation of the result. We can also move from the here, and this is important because we can have, as we have degradation, we can need for specific years extra electricity or extra carrier for any of them. So in this case, we need an extra electricity from the grid or for the renewable once we start to have degradation of the photovoltaic and also extra consumption of the electrolyzer. So I will go to the operational result and just show you. So I want to know what is the real dispatch of the electricity. So I will go and add a new graph. I will select my electricities. I want to select the photovoltaic, the wind, and the grid. And I want the production of the grid, of the wind, and the PV. So now I will just change the scale because here I'm in an early resolution. I want to see a typical day per month to have a quick view of the profile. And I will just change some color. So here for the grid and the PV, I like to have it in yellow. Okay. So here we can see how the system will behave in terms of electricity supply. So we have a base load almost of of the grid. Then we have a huge production of solar during the day, of course, because we have like 2.3 gigawatt of installed capacity of photovoltaic, and then we have the wind also that can cover during the night. So I will save it, electricity mix, and I will save the graph. Now we can also have access in terms of operational result of all of the details of any of the component for all of the years. For example, we can see that for the photovoltaic, so it's a summary. So we have its capacity, its total operation per year. So for the first year here, and also the maximum capacity factor that we have and the curtailment. So we can see that if we move to the years, we start to decrease the operation of this plant due to its degradation. And we have no replacement for this component in the input that we put. So we are just decreasing the total operation. We can see, for example, I will just review the electrolyzer. So the electrolyzer here. Okay, so we started with this consumption of megawatt hour per year. So this is based on the 50 megawatt of electricity to produce 1 ton of hydrogen that we inputted as efficiency. And we can see that along the years, due to the degradation, we start to increase its electrical consumption. So here we increase up to here, up to the replacement. So here we have the replacement of the stack of the electrolyzer. So in the cash flow, we will see that we have a repex for this year. And then the efficiency goes back to the original value. So we can adjust completely the replacement that we want. We can, here we just select one replacement, but we can have like 2 replacement, one here and one here, for example, depending on the cost. And we can also see, so for the storage, we also have access to the quantities of cycles per year. So this can be useful to track the degradation, for example, that we need to consider for a BESS. So before going to the economics, I will just go back to my case and I will change it completely. So here was my base case. I will duplicate, and no, I do not want to, so base case with BESS. So I want to consider for the tender that I can have a BESS. So I will go here. So no, I will directly go, and in standard, in electrical, you can see that I have several components. So I will import a BESS. I will just check that the carrier are the same. Yes. And now here is my battery. So we can see that we have a capacity capex and charge capacity capex, and we also have a capacity opex. So these two different is to represent one, the capacity in terms of storage, so the cost per storage, and the other one, the cost for the power, so for the inverter. And in this case, as it's an electrical battery, so we add to use the charge and discharge efficiency, and the same for the charge and discharge rate. We also consider that we do not want to go below 20% of the state of charge of this equipment. So I will just move it. And also for the tender, I know that I cannot have access to a grid take or pay. I will have to use an off-peak and off-peak system. So I will just do as before. I will delete this one and I will import in electrical and on-peak, off-peak. I will just, so I will have 2 new components, grid on peak off peak, and that will produce electricity. So I will change because I want them to produce electricity from the grid, not electricity. Okay, so now I have here my on peak with no cost. So we will see why we have no cost here for this equipment, and the same for the off peak. So I have no cost because with this component, I also have, as it's on peak and off peak, I have specific profile. One for the availability, that it's an operation max as well as for the other one, and one for the cost. So if we review the profile, so I will just go with the on peak and off peak availability, and I will go to the hourly resolution. I will just show you in for 1 day, so the first day of the year. So here is what is my profile. So I have the grid off-peak availability, that so it will be available at 100% during the first hour, so up to 2 a.m. in the morning. Then it will be the green So it will not be available anymore, and we will have the availability of 100% of the on-peak. With the exchange during the day, it will be the opposite. So we'll have access only to the off-peak and not to the on-peak anymore. And it will be, so here we define it as cyclic, so every days are the same. And we can also see what we inputted for the cost. So here is the cost structure that we fix for the off-peak and on-peak. So of course, the off-peak has a lower cost. So here it's a low cost during the first hour of the night, and a very low cost during the day, assuming that this off-peak is mainly used by renewable supply in the electrical market. And for the on-peak, is the opposite. So we are reaching a top of 120 US dollar per megawatt hour at the beginning of the day, and the same at the beginning of the evening. So what I also want to do, because the tender has some specifications regarding the maximum emission that I can have for the system. So I will activate the emission parameter, and I will go to the grid, so on peak, and I know that this as an average of the year, so let me up, as an indirect emission factor of 0.8 tons of CO2 per megawatt hour. And I will also save for the off-peak. The off-peak is lower as I said, there is a lot of renewable energy in the system, is 0.3. I will save it. And now I will optimize, so I will just have a look again to the system. So I have my battery, I have my on-peak and off-peak. So this was the major change between the base case and this one. I left the same amount of ammonia that I want to produce. And I will go to optimize. So now, as I have emission, I can activate that I want to calculate the emission. I will go in early basis because the tender does not specify if I need to do the calculation and to show the certificate in an early basis. So I will leave it in early, and I will optimize. And so now that it's optimizing, to keep the meeting in track, I will go to see back the result of the base case. So just to remind, the base case has a grid take or pay, a PV, and the wind only for the electricity part. And I will go to the economics. So in the economics, the first data that we can have is that we have the summary table of all of the investment that we'll have to do for the equipment. So we can, for example, sort it by the higher ones. So we'll have the higher investment will be in the wind and the PV, and followed by the electrolyzer. So we have the total million of dollars that we'll have to invest for each of the component. And then we also have a tab to calculate and to review the levelized cost. So here we have the main net. So a subnet, it's to calculate other kind of levelized cost. In this case, as we selected ammonia, that was the only demand that we had in the project, we have the automatic calculation that consider all of the cost of the system and discounted by the production of ammonia. So we can review directly the waterfall. So to have a quick look about the distribution of the cost of this levelized cost of ammonia. And we can see that we have a huge proportion of the wind and the PV, followed by the electrolyzer and the harbor portion. Then we have less and less contribution for each of the component. We can also review the cost breakdown if we just want to see in terms of CapEx, or we can view the REPEX and OPEX as well. So if we let just the REPEX, the only REPEX that we had was for the electrolyzer once for the lifetime of the project. So we'll go back to that. And for the tender, as always, I need to provide not only the final levelized cost of ammonia that I want, but also the levelized cost in the intermediate one, so the levelized cost of electricity and levelized cost of hydrogen. So I can do it. I will first calculate the levelized cost of the grid. So we'll select the grid and its extra electricity. And I will go next. So here I will start to calculate some sub-levelized cost. So I need to go value chain by value chain. So here I will do the same with the renewable. So I have my two renewable. I will leave everything automatic. Then I can calculate the the weighted average at the end of levelized cost of electricity of the system. That will be the levelized cost because all of those components use this electricity. So I need to know exactly what is the cost of this electricity. So here I will just select this electricity mix and electricity. So now I need to input some cost for the input, so the feedstock. So for the renewable electricity, I will just select the one that will be calculated, and I will do the same for the grid. So I will calculate those costs before moving on with the electrolyzer side. So this is very useful if we want either to answer a specific question of the tender or if we want to be able to compare projects that are not producing the same molecule at the end. So we can see the levelized cost of the grid that is higher than the $80 per megawatt hour that we fix as an input, but this is only due to the fact that this grid take or pay was not used as 100%. So the cost is the same, but we have less production. So this is why we have an higher cost. And we can see the levelized cost of electricity of the renewable and the weighted average, as we saw that, and we can see that the level of production are quite different in order of magnitude. We have a total levelized cost of electricity close to the renewable one. So now I will just quickly continue and I will calculate the levelized cost of water. So to do that, I need to select the seawater and the desalination plant. And I want to calculate based on this, and the only producing is the desalination water. So I need to select the electricity that will be accounted for the cost, and is this one. And now I can finally calculate the levelized cost of hydrogen. So for the levelized cost of hydrogen, I will just select the electrolyzer and the compression. And this one. So I will consider this hydrogen, and that the only producing will be the electrolyzer. So, and I want to consider electrolyzer from the electrolyzer because it's the only producing really, because this at the end the hydrogen will be produced only by this plant. And I need to select what is the electricity, so this one, and what is the cost of the water. And I can calculate again. So we can do, of course, the same with the levelized cost of heat and then the levelized cost of ammonia at the end, if we want to have everything separated. But in this case, in the sake of time of the webinar, I will just keep in the levelized cost of hydrogen. So in this case, we can answer to the tender that will have a $4.6 per kilograms of hydrogen, and we have all of the detail if we want. So mainly all of the cost is driven by the electricity consumption. Then we have the capex, repex, and opex of the electrolyzer, and we have a small contribution of the water and the hydrogen tank in this case. So all of the configuration can be downloaded if we want to import to another case quickly, and we can also download, I will download some of them, all of the result. So this will consider all of the cash flows mainly of everything in Excel if we want to do our own analysis outside of the tool. So I will now go back to the case with Bess, and I will open the result. Just to recap a little bit, so this is to answer to the tender that has some restrictions regarding the grid and the quantities of ton of CO2 that can have my end product. So I want directly go to the operational result. In the emission tab, I want to see how much I have in terms of ton of CO2 per ammonia. So I have 2.3, 2.9, so ton of CO2 per tons of ammonia. And this is mainly because of the cost and the structure of the grid on peak and off peak. As I have no restriction, I'm mainly using the grid off peak as a main production. So the photovoltaic and wind are very small, and I have a very small battery. So this, I want to be sure, and I want to know exactly what will be the difference in the system if I restrict the total amount of CO2 that can have my end product. So I will go without duplicating the case. I will just go and make some adjustments. So I will have a new scenario and I will put emission limit. So I was at 2.9 at the base case. I will put 2.5 and I will go to the emission. I will select the ammonia carrier. I want to limit the at gate, so the limitation, and I will put 2.5. Then I will duplicate because I want to make some sensitivity. So I will put 2.5, I will put 2. I will just leave it at 2. So we can do exactly the same by downloading an Excel and uploading, but as I'm just doing some of them right now, it's quicker to do it like that. So I will put 1, 0.5, no, I will leave 0.3. And for the last one, I want to see what will happen to my system if I'm limiting to use only the grid. To use only the renewable profile. So if I'm limiting to 0 tons of CO2. Of course, all of the value here. So here I'm just changing for each scenario one parameter, but we can add several ones. For example, I can also add that for this scenario, I can change also, for example, for the supply, that the off-peak parameter, so if I go to the emission one to keep it in emission, that the factor, the grid, so the emission factor of this parameter for this specific scenario is not 0.3, but it's 0.2, for example. But to keep it simple for this demonstration, I will just leave everything empty. And then I will save them and start to run them. So here it should take 1 minute per scenario. So I will not wait to out of the scenario to finish, of course, otherwise we'll lose a lot of time. And I will directly jump to the other use case. So I will leave it here to see what happens at the end of the optimization. So then let me move to the use cases with ANDREA Nation. So we already saw one, that is the use case of we want to answer to a specific tender with a limitation in terms of tons of CO2 per tons of product that we are producing, knowing that we also have some restriction in terms of the water supply. So we needed to have a desalination water and that we had to use a grid on peak and off peak. So now we'll see another way to use ANDREA, and this is another use case. So in this use case, we will try to see if our system is resilient enough based on the first sizing that we do. Why? Because usually when we perform the sizing, as we have renewable profile, we are using a TMY, so a typical meteorological year. So we size all of the system, so the 30 years of the operation based on one profile, that is an average one, usually. So we can, of course, change, and instead of sizing with the TMY, we can use one with lower production, like a P90% or P5, depending on the convention. But we usually use a TMY. So here we see how we can use ANDREA to test if the system is still capable of producing what we were aiming for. So we'll move to ammonia. So from ammonia to power to mobility. So we want to produce hydrogen only based on solar and wind. We can also have a battery. So we'll be an off-grid system to a truck fleet. So the purpose of this example is to size the system using the typical meteorological year. Then we will check if the optimized system is also feasible for other years, because we have access to an history. So we will check if other years of PV and wind make the system feasible, and if not, we have to quantify it and make the adjustment to avoid the system to be infeasible. And we will see how this works in ANDREA as well. So we'll first start by the slide. So this will be the system that we will see. So we'll have a PV off grid and the wind off grid, the possibility to have a BESS, so a battery electrical storage system. We'll have the electrolyzer, a compressor for low pressure, a compressor for high pressure, and then we'll have our hydrogen demand. In this case, we have a fixed demand for the hydrogen curve, so for the truck fleet, So we have during the day. So here it's in UTC, but the data represents place in India. So we have to consider that this will be the day here. So we need to produce or to supply the hydrogen to the demand during all of the hours of the day. And this is the typical meteorological year for the place in India that we have for the photovoltaic and the wind and the wind. So based on that, we first run the basic optimization to find the optimum sizing of all of the component. Then we obtain, as it's a small case, we obtain close to 800 kilowatt of capacity of PV, 60 kilowatt for wind, and a small battery. We also have a small electrolyzer size with 300 kilowatt of electrical capacity. We have the side, so the main size of the storage as well. But this is considering the typical meteorological year. So we need to be sure that after that, the system, if we consider other years, will still be able to produce. So what we did, we went to the library of profile that we have, and for the same place, we also downloaded and we imported into ANDREA 18 years of profile. So we can see the repartition of the deviation at the end of the PV profile and the wind profile. So we have a huge deviation in terms of average. So here it's the typical construction of the minimum, maximum, and all of the percentiles of the profile. So it considers that the minimum is for each hour of the profile. So it's not the minimum profile. So this is why those values are lower than the worst year, because it's a synthetic year at the end. So we have a huge variation for the PV and also for the wind. So with this variation, we want to be sure that the system is feasible. So based on that, we run the calculation. So we were able to run sensitivities on the base case with the fixed size with all of the years. So we had to include a kind of failure system just to be sure to quantify how much electricity in terms of power and energy was missing to the system to make the system feasible. So we can see that for all of the years that we had only 7 years with infeasibility. It means that this failure supply of electricity need to be activated. We can see that the power, so in the right axis, is quite the same for all of the cases. So around 200 kilowatt of needed power for this failure supplier, but the energy it's quite different. So we have for the worst year, so the year that use most of the failure, close to 50 gigawatt hour, and the year just before the infeasibility at the end, so the last year that is not feasible, we have a very small amount of electricity that has to be used. Then we can go to ANDREA and see what happens and how we can do it and go quickly to the result. So in the meantime, all of the simulation here finished, so we can directly see what will happen to my main levelized cost if I'm changing the CO2 emission limit and go from 2.5 to 0 if I just want to use the renewable energy. So this is just to answer to the previous use case. So I will go back to user cases. Now we close those ones. Okay. So let me open this one. So this is the base case of so we will see. So it's locked. So this is the same representation of the case. So we have here the wind, the PV with the battery. We have the water sources and the failure component that will be used only if we are missing electricity. And we have the two compression system, the two storage, and the demand. So we can review that here. This has been first optimized, and then we fix the capacity. So we can go and see that the electrolyzer, for example, has a fixed capacity. In this case, we want to keep this simulation with 310 kilowatts of electricity for the electrolyzer. So all of the components are fixed as fixed size, like in the presentation. So, for example, we can see the 60, the sorry, 820 for the PV and also the BESS. So once we have the base case, I think that is this one. No. So I will go and open the result just to show you. So we can see first that with the base case, we do not have here the failure supplier because the base case has been optimized knowing the typical meteorological year, but it's the same profile used. So we have no need. So all of the components are sized to meet this electricity. So we can just see what happens in terms. So first I will show you the demand profile. So the truck, that was a fixed one. So the consumption, so it was exactly the same. So we were respecting the fixed profile that we inputted. And I will also change, and instead I will just go to the renewable, and I want the PV and the wind. And I want to see the production of those two. Okay, perfect. So this is the typical mix of my system in the base case. I will leave it like that. So now that we have everything optimized, we are very happy because everything works in the typical meteorological year. So we went to the multiple optimization and we uploaded. So it take times. We uploaded for. So if we go to profiles, each specific year of profile. So the PV and the wind for the year 2016 and all of the 18 years that we have. We also make some other adjustment if we want to go deeper into the analysis. So if we go back to this, so we have one scenario for a specific year. So we can see directly the main net, so the levelized cost. We can see that some of them has a huge levelized cost of hydrogen. And this is why, as we inserted into the case a failure supplier, the failure supplier need to have a high cost, otherwise the system will try to use it. So this is a cost to avoid using it, but to make the system feasible, to be able to review all of the analysis. So we have here, this is the worst case. No, sorry, it was 20. Yeah, this is the worst case. So we can see that we have several of them that are exactly the same that were in the presentation. So we can go, for example, I created a comparison. So I selected all of those cases and I'm here into a comparison module where I can start to create my own table of comparison. So I can go to the failure one. So here I just consider for those cases that I want to see in this table, the total production, so the total operation of the failure supplier and its maximum capacity. So I can see that all of those cases, what was the amount of power needed by the supply, by the failure supply, and the total energy that I will need. So this is to help to understand which will be the worst year. So I will go to this one that was the worst year. So we can see in the result that we need. So the failure is here in the optimum design and we need it. So we can go and see in the electricity mix what happens. So it's not used almost, so it's not used. Let me go back to see exactly the percentage. So it is used only 2.3% in capacity factor. So very small amount. So we need to see. So in operation, so it's mainly used here. So in the morning in February and January and March. So now we can also try with this one that is the almost feasible one. So the last case that is in feasible. And here we can see that we have less usage of this failure. So then we can go back to the base case, that is this one. And here, what we change, so we select all of those years that were not feasible, and so we left the same year of the profile, but we change. So we change the battery. So the battery has no a size that can be optimized instead of the fixed capacity that we had before. So for each of them, just to be able to have the result of what will be the optimum configuration of the battery, so the optimum size to make the system feasible in this case. And based on that, we can see the impact in terms of levelized cost. So this was the worst year. So here we have the worst year's capacity of the storage. So it's the year that has the highest impact in terms of levelized cost. And just to finish before the Q&A session, then what we did, so we went back here. So the worst case is this one, just to have the impact. So here we fix the size of the battery based on the sensitivity that we did, where we optimize based on the worst year the size of the battery. So it's the fixed capacity here. But then here we use the typical methodological profile to be able to compare the result. So here we have, for example, the result in terms, so comparable because we are using the same typical methodological profile for the PV and wind, but we are using the oversized battery just to be sure that we can supply enough electricity to all of the years of the profile that we had for this location. Then we can, for example, go to the result and review and compare with the base case what happens in terms of operation or in terms of levelized cost. And that's it for the second study case. So I don't know, Paulo, if you want to go back.
You can go ahead, Luis. You want.
Okay, so at the end, what we saw is how we can use ANDREA to help in the design and in the review of the project. So we can be in an early stage, so in the scoping, so in the definition of the to find the best size and capacity and all of the operation of the system, and also to start to review scenarios, because in the real life it will not be a typical meteorological year, or all of the year will be different. So we need to be able to size some scenarios. We can also, in the sake of time, we could not see it in this presentation, but we can also make some scenario analysis, changing the technology. So some specific technical characteristic of the electrolyzer or any of the component, just to be sure that the system, and to see what will happen to the system if we change them. And with that, we can review the feasibility of the system and all of the results. We also, so if we are in a more advanced step of the project, we can check if the system is compliant with the regulation of the market or the tender that we want to participate. It's also important to take this into account at the early stage of the project, just to be sure that the sizing is done accordingly to the tender or the regulation that we are aiming to. And we can also use ANDREA, of course, to review in a RFQ process, to review what will be the impact of one vendor versus another one in terms of technical characteristics. So what it will be the impact in operation of my system or the levelized cost. And what we offer, so we in Hinicio, ANDREA, as Paulo said, so it has started as an internal tool, but we also offer it right now as an external. So we offer a license to use the exact same version that we are using in our own study. So you can purchase a license that you will be able to do exactly the same as us. And we're also offering some augmented consulting packages. So this is to train not only on the tool itself, but on the methodology that Paulo explained at the beginning, so the system engineering, because a tool is just a tool, so we need to be sure that the tool will be used in a framework of a methodology to avoid just simulation without any purpose basing on the methodology. So we are offering both, so the license and the augmented consulting part in Hinicio. And that's it for the presentation today. We still have 10 minutes for the Q&A. Thank you for your attention.
Thank you, Alois. This is a fantastic presentation. Thank you, Paulo, for answering several questions online as well on the chat box. We open it to the floor for if anyone wants to ask questions, but perhaps I can lead with one. Alois and Paulo, this seems like a fantastic tool giving a lot of inputs and scenarios based on the user's parameters. This seems to be very useful for several function leads, for project designers, for procurement and supply chain leaders, for business developers who are submitting responses to tenders or commercial offers to customers. If someone wants to have a deeper demonstration of this particular tool or contact you for getting a license, how would they do it?
So there are
Oh,
several
sorry.
options. I think for example, you can access to the webpage that's available right now that we are sharing the screen, and then you will find some contact information, and we can go directly to you after that. Or feel free to reach me or Alois in case you want to access to another like more personalized demonstration, maybe, or with more information about Andrea. We will be more than happy to organize a separate session in order to cover all maybe doubt that you may have.
Thank you. I'm sure this is
Mm.
very useful for all of our participants here. I'll open it to the floor. There are about 5 or 6 more minutes. We can have a few questions in addition to what Paulo has picked up on the chat box. So if anyone wants to ask questions, they can either put it on the chat box again or unmute themselves and introduce themselves and ask the questions, please. Paulo, in the interim, are there any questions from the chat box that you've picked up which you found very interesting that you would want to verbalize?
Good one. That let me check 1 second. I think one point that I always want to highlight is the possibility in Andrea to modify the time resolution. So sometimes, depending on the objective of your analysis, sometimes you need to find the optimal sizing for your complete value chain. Sometimes you need to do more feasibility analysis of your current configuration. And for doing that, it's more appropriate approach to have different time resolution, meaning that for sizing definition, we always recommend at least an early resolution on a yearly basis. But for example, if you need to know if the solution proposed by a third party is it's able to to keep the operation up and running when you have some unexpected scenarios. For that, we recommend a lower time resolution. It could be, for example, a 15-minute resolution for 2 weeks, in which you have more precise forecasts about all the renewables, and you can also define the ramps up and down for your equipment with a better accuracy and so on. So being able to do that in Andrea and being able to do that all at once with the tool, I think it brings a lot of value overall.
Maybe also, I don't know, Paulo, because I did not have the chance to
Mhm.
look at all of the question of the chat, but the questions regarding the data. Do you know if you answer one of them or not? No?
Yes, we answered one question about data, but maybe if you
Yeah,
want to
okay.
elaborate on that, feel
Yeah.
free to do it.
Just just to remind that at the end, Andrea is very open as a framework. So all of the data can be changed, and it's the responsibility of the user to enter the data. So we all often have the question on how can I change, how can I input the data? So we also provide separately. So as I show when I was importing data, so I was using a standard collection that has only dummy values for demonstration, but we can also cost separately a collection of specific set of data just to help you in importing a real world data and compare with the one you have. So to help the user to access the first class data and use them in the case.
I think Alois and Paulo, this has been a fantastic webinar and an introduction to Andrea by Hinicio. I'm sure there will be plenty more questions, and some of our members, participants, and stakeholders would want to get in touch with you for a dedicated demonstration and more questions and clarifications also. I'm sure they will get in touch with you. But nevertheless, a message for our stakeholders. We are very pleased to collaborate with Hinicio. This is a part of our Green Hydrogen India webinar series, the third such in 2025 so far. All of our webinars as well as our physical events are recorded and uploaded onto our YouTube channel, GH2 India. Please feel free to reach out there, and feel free to reach out to any member of GH2 India as well as Alois and Paulo for the brochure or further details and to get in touch for a deeper conversation on Andrea by Hinicio.
Perfect. Thank you so much, Arjun, for the G2 India for organizing this session and invite us to participate in this. We really appreciate it.
Yes, thank you very much. It has been a pleasure to present to all of you the Andrea features.
Thank you so much, Leos and Paulo. I wish you both well and good luck to Andrea by Hinicio.